So, good morning everyone and welcome back. My name is Ben Callow. I'm a postdoctoral researcher at Ghent University. I'm also a geologist. I'm from the UK and I've spent 5 years in research of digital image processing of rock. And please forgive the pun, but I'm excited to provide you with some tips and tricks when it comes to image processing and to share my experience with you. So first, to pick up from where Jan left off, if the reconstruction process has gone well and all of the projections are correctly aligned with a good center of rotation, we should end up with an image that looks like the one on the top right-hand side of our screen. And from this series of 2D images to comprise a 3D image, we can then commence with image processing of 3D images. So before I dive into the details, I'd like to first present to you some sexy animations of a sandstone case study to highlight and give you an overview of what is possible with image processing. So firstly, a case study of sandstone. So from a grayscale 3D image, after filtering and segmentation, you can isolate and characterize the pore space, which is shown in red, and then you can remove isolated pores, which are shown in white, to leave just a connected pore network shown in blue here. Then we can undergo pore separation using a skeletonization algorithm to generate a pore network model of pores shown in red and throats, which are pore connections shown in grey, sorry. And finally, we can go one step further and undertake image-based fluid flow simulations in both the horizontal and vertical plane. So image-based simulations can be very good, for example, if you want to generate physical properties and use them as input for upscaling in upscaled models, or to compare these property calculations with laboratory experiments, or indeed to compare them with dynamic imaging, which Mustafa is going to talk about a little bit later on. But let's not get too ahead of ourselves. So I received some good advice from one of my previous supervisors at Southampton University, Ismail Falcon Suarez. He said, Ben, you need to make sure that your 3D image analysis is accurate, otherwise you'll be publishing art and not science. And as lovely as those video animations were, I did tend to agree with him. So the solution for that would be to optimize the X-ray image processing workflow. So that's what we're going to do. And I'd like to share my insight with you now. So the challenge and why we do image processing is to quantify properties of complex 3D porous or granular materials, or indeed mineral composites, or also biomaterials, which may not otherwise be possible by hand, such as measuring grain size manually. Now, so there are a number of different 3D image analysis software out there for this purpose of processing, such as Fiji or ImageJ, Aviso, Dragonfly, which have all been very good to me over the years. But it's also worth noting that there are a wide range of open source software and commercial software available. So to talk through the image processing stages, this is the simple setup that you see on the bottom left. So you start with a grey value image, then through segmenting or thresholding, you generate a segmented image, and then you can go one step further through object identification to characterize individual objects in your image. And in this bottom series of images here is an example of foam. So now I'm going to take you through this image processing stages step by step, beginning with grey value analysis. So first you should ask yourself, what is a grey value image? So if you have a 2D image composed of pixels, or indeed our 3D X-ray image composed of voxels, they each have a grey value which is dependent upon their attenuation coefficient, as described previously. So here's an example of a sandstone. So you see here areas that are represented by grains in grey because they have a more higher attenuation coefficient, but there are also regions in black which are represented by pores which have a lower attenuation coefficient. This is an 8-bit image, so it has 256 possible grey values, but 16-bit images are also commonly used. So if I show a graph here of grey value on the x-axis versus frequency on the y-axis, in an ideal scenario, if there was no noise in our image, we might expect to see a histogram like this. So there's a histogram here which represents two peaks. The black peak first represents the pores, and the second grey peak would represent the grains. However, it's not always quite as simple as that, because in reality our X-ray images do contain noise. So what we get is something a little bit more like this, where you have two peaks, but they overlap quite significantly. So therefore, it's our job as image processors to distinguish between the two phases. So immediately we can make life easier for ourselves with this challenge. And the first step is to do noise filtering. So contained within standard image processing software are filtering algorithms used to remove noise, such as a Gaussian filter, a median filter, or a non-local means filter. Now, each filter often has what's called a kernel, and as you increase manually the kernel, it depends how aggressively the filter is applied to your image. But note, and what's worth bearing in mind, is to be careful not to overfilter so that you don't inherently change the true geometry of your material. So I'm going to give you an example here on the screen. So on the top right you have a Saviniera limestone, and on the bottom left you have a histogram, whereby the first peak represents the pores and the second peak represents the grains. Now look what happens when I apply a median filter. So you'll notice two things represented by the now red dashed line. Firstly, the peaks become more prominent, and secondly, that overlapping region becomes smaller. So therefore, you make it easier already to segment the data and distinguish between the two phases. So I mentioned segmenting the data, so let's get straight to it. So I'm now going to present some different types of ways to segment your data, starting from the more simple to slightly more complex and advanced. So firstly, I'm going to talk about thresholding. So thresholding is often used to produce binary data, which means data that's either in one phase or another. And you can use something called a simple grey value threshold. So again, I'm using my trusty Saviniera limestone as an example. And I've got, again, our histogram of grey value versus frequency, with the first peak representing pores and the second peak representing grains. So now if I used a simple threshold, this is all I do. I set manually right in the middle of the two peaks, and then anything to the left of that threshold line would be segmented out as pores, and anything to the right of that threshold line would represent rock. So that seems quite simple, right? But in reality, our X-ray images are a little bit more noisy with a bit more overlap. So we want to use a little bit more advanced techniques. So now I'm going to talk to you about region or morphology-based segmentation tools. And one of the main examples in this category is the watershed segmentation, which I'd like to now describe to you. So again, my Saviniera limestone on the right and my grey value histogram on the left. To perform a watershed segmentation, this is how the process works. You would first manually assign a lower threshold range to all the areas that you're confident that are pore space, and then you would go to an upper threshold range where you're confident that it represents grains. And now the challenge to deal with the overlapping region in the center, which is where the magic of the watershed segmentation comes in. So first, I want you to visualize this image on the right-hand side and imagine it in 3D. So imagine the black represents trough regions, areas of downwards, and the grey value represents peaks. So if I visualize it here down below, so again, those troughs represent more of the darker regions, and the peaks represent grey regions. Now you can think of this three-dimensional picture as like a drainage basin, okay? So in a drainage basin, you have rainfall. And if you were to pour water on this drainage basin, you'd reach a watershed line. And then anything below that watershed line would represent segmentation of pores, whereas anything above that watershed line would represent rock. And this is what's known as a region or marker-based approach. So now we can get into some more advanced segmentation techniques, an example of which is using supervised machine learning. So I want to give you an example, and one is using the trainable 3D Weka segmentation that is available in Fiji, but there are also similar techniques now available in Dragonfly. So the same principles apply. So here's what you would do. This is an example of a very heterogeneous sandstone sample. Forgive me, I do like sandstone. And I'm going to take a very small 100 cubic voxel volume region of this data set. And then within this region, I would apply manual annotations of what is pore and what I believe to be rock. And then I would train this data set. Now, from all of the manual annotations and training combined, this is called a classifier. And then once I've trained this classifier, I would then apply this classifier to the whole volume of my sample. And you can do this using something called a tiling algorithm, which is all plugged into the software. And then what you can end up with is quite significantly good results. In this case, it worked very well. And what's worth noting is from that small classifier, you could not only train this sample, but if you had a collection of samples that were all like this one, you could use the same classifier for a full data set. So this is quite a useful tool. So I've talked now a little bit about segmenting into two phases, which is known as binarization, shown by the middle image here. But it's also worth mentioning that you can segment into 3 or more phases using the same techniques that's just been described. So you may want to segment into 3 or more phases if, for example, you have a very compositionally heterogeneous material, or indeed if you're working with a sample that contains multiple fluids, different types of fluids that you want to segment. So using this example, what we have is a heterogeneous sandstone that contains a high proportion of clay minerals. Now, what you'll notice from the histogram is that these clay minerals have created an intermediate peak between the pores and grains that could be segmented out using the segmentation technique shown. And this was quite useful in this case study because the clays contain microporosity, so 60 to 70% microporosity, not resolved by the CT image, that could then be factored into our object property calculations later on. A little bit further to segmented data, what else can we do to it before we're ready for the final step, which is labeling? Well, there is something called process operations to segmented data, also known as binary operations. These are simple mathematical tools that are used for cleaning up our data set prior to the next step of labeling. So I've shown an example here where there's a binary operation called removing isolated voxels, and it's quite simply as the name suggests. It removes all the small isolated voxels to clean up our image, ready for the next object labeling process. And in white shows a connected pore network, and in black is the background rock matrix. To give you another example, there's something called numerical coarsening. Now this can be a useful technique. If you have an image, for example, on the left-hand side, which is 1700 cubic voxels in dimension and a very high resolution, numerical coarsening is a technique where you downsample the resolution and lower the resolution and number of voxels in order to, the benefit of this is that it improves and reduces your computational time and also reduces the memory requirements of your computations. So this can be a useful technique, but just be mindful that you have to be careful with this technique that it could affect the accuracy of your end physical property measurements, but is certainly a technique that's worth considering with your data. Okay, now for the final step, which is known as label analysis. So basically we do labeling to identify different objects within our image. Now you'll forgive me, I'm going to use sandstone as an example again. So if I show you on the top left-hand side here, either in purple or blue, depending on your screen type, you'll see there are sandstone grains surrounded in black by pores. Now what we can do with this is we apply something called a distance transform. Now what this does is for every blue or purple voxel or pixel in your image, it calculates the nearest distance to a black voxel or pixel. So then you get something called a distance map on the top right, So the brighter areas represent a voxel, a blue or purple voxel that's furthest away from a black voxel. So you get this, what's called a distance map in the top right. Now what you can do with this is then apply a watershed, something called a watershed transform, which then allows you to separate and split up your objects into smaller parts. And in our case, it would be to split the grains into individual grains for further analysis. And then you might get a result similar to what's shown in the bottom left. These are separate images. But then you might see that the results necessarily aren't fully optimal. So you might choose to perform an additional watershed transform on your distance map to rejoin some areas to get a more desirable result ready for your further analysis. So I'm going to summarize the processing steps we've just talked through. So we have our X-ray gray value image. We can then filter the image to remove the noise. We can then threshold the image. We can then, to this segmented image, we can apply a distance transform and a watershed transform in order to separate our labeled image into a series of disconnected objects for further analysis, which can then you can perform a range of statistical analysis on these separated objects. So from this point onwards, there are a range of physical properties that you could calculate from this type of data. I'm going to give you an example here just of geological applications, but the list of physical properties is quite boundless. So for example, for geological applications, I would look at something like calculating porosity or connected porosity, or even look at grain statistics like their sphericity, their diameter, pore connectivity, etc. So there's lots of different object properties that can be quantified from your data. Now, just as a final slide, I'd like to just give a really brief introduction to image-based fluid simulations, and just to make you aware of them. So there are two main types of finite element method simulations, one of which is voxel-based solver, and this is where you directly use your segmented image as input for a fluid or image-based simulation. And then you also have what's called a mesh-based solvers, and this is where you have your segmented image, you undertake a surface extraction of that segmented image, and then from that surface you generate a tetrahedral mesh. Now these tetrahedral meshes can be very useful for computational fluid dynamics simulations. But these types of simulations can be very good because they give you fluid or object properties that you can use to compare or use for model upscaling. You could use to compare with your laboratory experiments, or you could indeed use them to compare or complement some 4D dynamic image experiments, which Mustafa is going to talk about later on. Okay, so concluding slide and a summary of my top tips for you. So firstly, the gray value of your image is based on X-ray attenuation, and grayscale images can be segmented into 2 or more phases, and see Viola's upcoming presentation on some more compositionally complex materials. Secondly, try to make the smallest amount of modifications, such as filtering to your image, as necessary to extract the data you need. Thirdly, try to optimize your experiment first for your segmentation. And I would encourage you to see Lorenz's upcoming presentation, which explores this idea further. And finally, when generating object properties such as porosity, permeability, electrical resistivity, also consider things such as representative size. And I would encourage you to see Jan's upcoming presentation on multi-scale imaging, which explores this concept further. So thank you for your time, bedankt voor je tijd, and I would welcome any questions you may have. So thank you very much for your time.